Good afternoon, everyone. This is Nathaniel, W2NAF at the HamSCI biweekly Telecon. And today is Thursday, November 11th. And we have a speaker today, Kike Rojas Villalba. Sorry about that. He is a postdoctoral associate at Cornell in the Department of Earth and Atmospheric Sciences. And so I would like to welcome Kike, and the floor is yours.
Great, thank you for inviting me. So I'm going to share my screen now, okay?
Sounds great.
Okay, let's see. Let me know when you can see my screen, please. Okay.
Starting.
Can you see my screen?
Yes.
Okay, great. Okay, so thank you for inviting me. We have talked a little bit through email, basically, with Nathaniel, exchanging some ideas, basically me asking questions to him. And I told him that even though the research, my main research here at Cornell is probably not extremely related to the HamSCI initiative, I am involved in a couple of projects that I think they are strongly involved or could be potentially involved. And we thought that maybe could be of some interest to you guys. Okay, so this is the title of my talk. It's very general title because it's these three topics that are not exactly the topics that I'm going to talk about. They are not exactly, I think, aligned. So I just wanted to label them as data-driven models and ionospheric physics. So okay, I try to make these presentations very informal. So sorry if it's too informal, and please let me know if you have any questions during the presentation. So this is the content. First, I'm going to use just one slide to introduce some questions and ideas. Then I'm going to talk about these 4 projects that I'm involved in that could be, I think, maybe interesting for some of you. And then some final words that is actually an empty slide just to comment a little bit about the projects. So first, the introduction. So as you know, the development in technology enables now to accumulate a lot of data. And once we have data, we can develop or apply data-driven models. But despite there's a lot of development using data-driven models, there's still some difficulties in applying them. So for example, maybe some pre-processing is required. Oftentimes it's a lot of pre-processing required. These data-driven models can be seen as black boxes. The comparisons may not be direct, and that's I'm going to talk about. One of the projects I'm involved in is related to this. Then also physics should be considered sometimes, but it's not always clear how. There's another project that I'm going to talk about that is related to this. And oftentimes that data may not be labeled. So here I'm going to talk about, I'm going to talk about projects that are, I think, related to these 3 last points. And just to start the discussion, this is, I think, a nice problem in where data-driven approaches could be useful, but the comparison is not that direct. So if this is an electron density profile, you know that shooting electromagnetic waves with an ionoson, you can build ionograms. And we have a bunch of ionograms from a lot of ionosons, but it's not easy, it's not clear how we can use the data from ionosons to make models or data-driven models of ionograms. And with data-driven, in this case, I'm trying to refer to machine learning stuff. So this is the first project I want to talk about is trying to predict ionograms using machine learning algorithms. So the general idea, as you know, from machine learning algorithms, so applied to this case, it would be something like we have some geophysical parameters, we give it to this model, which should be very versatile. And the idea is that this model can produce some electron densities. But unfortunately, we don't have a lot of data for electron densities. But we have a lot of data of ionograms. And so this project that I'm working with two Peruvians, Jasmine, he's an undergrad student in Peru, and Marco Milla, he used to be the director of Jicamarca Radio Observatory, and now is a professor at the Pontificia Universidad Católica del Perú. And we're working on this, and this is the main goal. The main goal is to try to train a neural network to learn how to produce electron density profiles from geophysical parameters, but only using ionograms. And we're trying to figure this out. But for now, one intermediate step that we thought we had to solve first is to model ionograms. Because once we model ionograms, then we can, I think it's easier to target predicting or modeling electron densities. So we have been working on modeling ionograms. Here you can see the type of input parameters that we put in the model, stuff like hour, like KP, AP, F10.7. It's a very general set of inputs for a neural network. And what you can see here, these are some of the estimates that the neural network gives for the ionograms. These lines here correspond to the blue lines correspond to the estimate, and the orange lines correspond to the data, to the actual ionograms. And as you can see, the ionograms, the first version of the model didn't know where the frequency stops in the ionogram. So we had to use another neural network to teach it. To train it in order to find the point where, or estimate the point where the ionogram ends. And we have done several tests so far. So as you can see here, for example, the black dots correspond to the ionoson data. The blue dots correspond to predictions done with just 1 month of data. These predictions come from the neural network, this coupling of these two neural networks. And you can see they are pretty good so far. Here we compare these estimates with IRI, which I'm sure you're familiar with IRI, and also with SAMI2. And SAMI2 is a numerical model, very sophisticated numerical model of the ionosphere. And we calculated ionograms from these both models and compare them to our estimations. And here you can see examples of good fitting and bad fitting, because of course this model is not perfect. We are still just starting to developing. So here, for example, you see the predictions from SAMI2 on orange, and on green, the predictions from IRI. Here, the black dots correspond to the ionoson, and the predictions are the pink ones. So they're very close. But sometimes they can go nuts. But even in the cases where the predictions are not that good, they often do it, at least on average, better than IRI and SAMI2. And just to emphasize, this is a model that was trained just with 1 month and 3 months of data. So that means that in principle, any ionoson can make its own predictions using this neural network. Here, there are some predictions of FOF2 of the different models that we trained. based on neural networks against the IRI estimations. As you can see here, IRI tends to overestimate a little bit the FOF2 predictions, at least for the latitudes around Jicamarca. And yes, here what you're seeing here is are some small histograms of how the error distributes in the ionogram estimations. So as you may expect, the errors are larger when there is when you are close to FOF2, right? And this first row corresponds to the training with just 1 month of data, and this second row corresponds to the errors of training 3 months data neural network. As you can see, adding 2 months of data decreases a little bit the errors here, especially around FOF2. So that's good. And so these are some open questions that we're working on. First, how to implement the loss function, or how to complete the neural network to predict electron densities now that our ionogram predictor model is more or less working. And then what is the optimal data-driven architecture, which is, in other words, what machine learning paradigm is optimal for this kind of problem. It's not very clear. Then, okay, so now I'm going to talk about a little bit about some spread F forecasting and numerical simulations versus data-driven models. So as you may know, spread F is a phenomena that was first seen in ionosomes and is caused by some instability called generalized Rayleigh-Taylor instability. And it occurs when you have a steep gradients in the plasma, in the ionospheric plasma, and gravity pushes the plasma, so produces some drifts. These drifts produces some electric fields. These electric fields produces another drift, and these drifts start amplifying the perturbations. So after a while, if you take a coherent radar and point upwards, you can see structures of the coherent structures above the noise level of the background. So here, for example, these are some coherent echoes from Jicamarca radar. And this is basically Doppler information of 3-meter structures. And as you can see, during the night, you can get a lot of turbulent related backscatter. And yeah, so this is the problem. And I'm working in this problem with, again, Marco Milla and Reynaldo, who is an undergraduate student in UTEC, that's a university in Peru. So with respect to the numerical modeling, what I'm using is a spectral solver. There is a work from a PhD student at Cornell from a lot of years ago, and he reduced the equations responsible for spread F into a much easier set of equations, this one. So I solved these equations. They're not very hard if you assume some, so these are already simplified. So if you start from a ionosphere like this, and where the electron density profile correspond to these 2 lines here, you can produce these generalized Rayleigh-Taylor structures here, right? After the system evolves a little bit, you have these depletions here in the electron density. And if you initialize the system with larger perturbations, you get stuff like this, and you get other depletions in the electron density. So the model is more or less running. Of course, this is a very simplified model. It's not comparable to other more sophisticated ones, but we needed just a reference. And on the other hand, we had to build the data-driven model. But before that, we had to first estimate what is the occurrence of this phenomena. And Jicamarca has this Julia radar, which is a coherent radar that measures Doppler from 3-meter structures. And it has been doing this for like more than 20 years. So there's a lot of data there. And it's very regular. I don't know exactly how how many days, but there's a reasonable fraction of days is working during the year. So Julia gives us RTIs like this. And so this tells us where the echoes are coming from and when. And to develop a metric of occurrence, we just like draw squares here in the RTIs and counted one when there is where the SNR was above certain threshold and 0 when there was not. So then we could build this more coarser RTI of occurrence and then just collapse it to just one measurement. So we can say here that all of these hours there was occurrence of spread F. In the future, we want to do this for different altitudes, but for now we are just collapsing everything to just one altitude. So we lose altitude resolution. So what we are doing now is trying to compare, to build a neural model, a neural network model that can be competitive to this other model, which is not based on machine learning, but it's based on regression, which is basically a simple neural network. So these people, Anderson and Redmond, they build an estimation of scintillation. And then they said, okay, with this model, we can estimate whether scintillation is going to be strong or not. And using that, we're going to say whether there's going to be a spread F or not. And how are they going to measure the occurrence of spread F? Watching ionograms. And they did that in this paper, and they found that the success rate of their scintillation model was 89%. 89% using this confusion matrix. And that's pretty good. So we tried to do something similar. We tried to use their model, but we didn't compare it with occurrence from ionograms, but we compared it with occurrence of Julia. And in doing that, we saw that there's a lot of false positives. So a lot of times where their model predicted that there's going to be a spread F and Julia didn't see any. So that's one of the things that we are working on right now. And also we are trying to train a neural network, but with Julia data. So these are some of the open questions that we're working on. So first, why we want to understand exactly what is the source of discrepancy between the scintillation-based model, the ionogram occurrence of spread F, and the Julia data. This is, I think, this is more or less known in the spread F community, but we want to learn about this. And also, of course, how the different data-driven model compare to each other, because this system is requires some memory. So we will have to explore some architectures that include memory, and we're working on that. Then, Nathaniel, how much time do I have? Excuse me?
This telecon goes until 4 p.m.
Okay.
If you talk for another 10 to 20 minutes, then have some time for questions.
Oh, okay. I was targeting for 20-25 minutes, but yeah, okay. I'm going to continue.
Yeah. Whatever works.
Okay. Okay, so then this third project is about ionospheric refraction tomography. And I'm going to talk a little bit about this. So this project I'm working with David, it's an undergrad from Pontificia Universidad Católica del Perú. And Marcos Inoñan is another Peruvian. He's doing his PhD at University of Washington. So as you may know, there's this old problem of doing tomographic reconstructions of the ionosphere, and what people have done is to discretize the ionosphere in chunks, small chunks of density, and then leave the GPS satellites or low Earth orbit satellites to pass and give you TEC measurements and then build a linear system. You go from the integral TEC integral to the linear system, and then you solve the linear system. And that's basically the problem that you want to solve, right? So if you have a satellite moving in through these points and this satellite shoots two frequencies, you can measure the TEC from this receiver. And in this case, in this particular ionosphere, if this is electron density, the TEC is going to look more or less like this. So a lot of people have tried to solve this problem of inverting this system and estimate the electron density. So for example, if you have a model ionosphere like this one, which is basically Chapman plus some structures, some depletions, using the MART, which is a multiplicative algebraic reconstruction technique, which is based on this algorithm, you can get this. If you use the work by Converiate 2007, which is basically saying, I'm going to try to solve the system as close as possible, but I'm also going to penalize some function of the derivatives. And then there's another approach by Lee, where he says, okay, I'm going to solve the system, but I'm going to penalize the derivatives in one direction, and I'm going to give another penalization to the derivatives on the other direction. So I'm going to look for smooth solutions. And there are some other approaches for this problem, but I think these are pretty convincing. But I think, so this is a regular tomography problem. And I started with this because I think people are more familiar with this approach to estimate electron density. But here we are in this project, we are interested in allowing the wave to refract. In these models, you usually assume that the wave is going in straight lines. So if you let the wave refract and you simplify the ray tracing equations a lot, as you know, you can get more or less a system of equations like this, which everything depends on the gradients of the electron density. So for example, if you shoot an electromagnetic radio wave from here, from this transmitter, is going to go up and then down. And if you see this trajectory from the different planes, you're going to see this. And sometimes if the electron density that you're using, it has some structure, you see these weird jumps, right? So Dave Heisel here at Cornell, he has worked a lot on trying to use experimental data and this model, well, actually a more complicated model, but in principle is similar to this ray tracing model, to then estimate the electron density. Here I put this paper if you're interested in this. And the idea is the following. If you have several transmitters and receivers, then you can connect them through these links, through these electromagnetic waves. So each receiver is going to see something like this. This is range, and the color is power, and also is going to accumulate information of the Doppler shifts. So this range is something that in principle can be calculated from the equations, and the Doppler shift as well. So if we can extract from RTIs like this information, like the time series that you see here, time series of range, time series of Doppler shift with some uncertainties, and time series of power variation. And we can have this time series for each receiver and for each transmitter receiver connection. And all of these points for each specific time correspond to a snapshot of the same electron density in 3 dimensions. So that's a system of equations that you can solve. So it's similar to the tomography problem, but instead of having a linear system, you have a nonlinear system of differential equations. And so you can do that. You can put this into the computer and you get things like this. So here, this plane here correspond to the, I think this is the HMF2 plane. And this value here, the color correspond to the maximum electron density. And I think this other plane is the HMF2 minus the scale height. So what we are interested in this small collaboration is trying to go a little bit further from Dave's work. So first of all, we want to see whether there are other numerical methods that could be more efficient to do this, because what he did in this paper, it was basically to shoot the wave a lot of times and try to correct the angle until you get to the receiver, and then try again and modify the ionosphere and try again. And there are some methods in optimal control theory that we're exploring that could be potentially, I think, more efficient. Then also, what is the optimal experimental configuration to reduce the ambiguity? Because it's not always clear whether we need, of course, if we have infinite receivers and transmitters, that's good, but there must be at some point some diminishing return, and we are exploring that. And also, and this is the main reason I sent this first email to Nathaniel, is how about using just ionoson receiver, right? So if you have an ionoson here, for example, that is a good transmitter and is shooting in different frequencies, for each frequency you can have a system of equations or a time series like this. And if you have low-cost receivers around this transmitter, you can, I think, build a much less ambiguous system to be solved. And finally, this is a small project that I'm collaborating with some Peruvian students and teachers. And this is a project that we're trying to use this platform. I don't know if you have heard about this Zooniverse platform, which is a web platform for citizen science projects, for crowdsourcing, data processing. And what we want to do is we want to put some ionograms in the platform. It's very easy to use, actually. So we already have a lot of progress on that, and so we're going to put ionograms that are currently not being scaled from one of Jicamarca's ionozones. And we want the people in Peru specifically, or Latin America, to engage in this scaling of ionograms. We have been thinking about possible ways to use this data. We're still thinking about this because there's a big question of how usable this data is going to be, right? So the general process is for an ionoson is to construct the ionogram with a Viper ionoson, for example, then some pre-processing to remove interference, denoising, stuff like this. But instead of going to the database or to automatic scaling software, we are going to try to do this by citizen science. So this is going to be uploaded to Zooniverse, scaled by citizen science, retrieve some statistics and iterate here, and then add to some database. And I think there could be some project that could be some scientific question that may be addressed for this data set. One of the applications that I am very excited about, possible applications, is as a training data set for machine learning training. So yeah. Finally, some summary and conclusions. Well, as you know, there's as you may notice, all these projects are being developed with Peruvian students and teachers, and so it was basically because of the pandemic that when the pandemic started, I started working this project. I suggested these ideas to these people, and we have been working, I think it was very productive so far. So this is one of the few positive outcomes from the pandemic, I guess. Very good collaborations, remote collaborations. Yeah, so this is all I have. Thank you.
That was very interesting. Any questions? See a bunch of claps going on. That multiple.
Excuse me?
Go back slide. Transmitters and receivers.
What? Sorry?
Yeah, Nathaniel, you're breaking up pretty bad.
I'll call in with the telephone. If
Yeah.
someone else can keep asking questions while I dial in and change audio connection. So I'll be back in a minute.
Mm-hmm. Sure.
Yes, I have a question concerning the ionosound data. Did you specifically use one set, or were you drawing from multiple sets, or how did you decide which ones to use?
So are you talking about the...
Yeah, you're feeding your algorithm data to learn from.
Okay.
Is it important to keep from one specific one such that the algorithm can learn its idiosyncrasies, or is it more important to feed it from multiple ones to learn the generalized idiosyncrasies?
Yeah, that's a good question, and I think it's a little bit of an open question for the neural network community. This is has its roots, I think, on very strange mathematical problems. What I could say about this is the following: just from experience, we have seen that so you know that the neural network is basically like a bunch of matrices. So you can understand the neural network as a bunch of matrix vector multiplications. And what the neural network does is it finds the coefficients of these matrices. And it seems that these numbers, they change a lot. So you really can't, you really need to be close to what you have to predict. So for example, if you want to make a prediction of the next few hours, you need to train your model from the previous days or hours as well. And it's not clear exactly how to capture the different layers of variability. So for example, as you mentioned, you have the geographic variability. We're using just one ionosound. So we shouldn't expect, I think, this model to be very geographically aware. And also we noticed that the more data that you put in the model, it's like you start to you don't get a lot of predictive power if you include 1 year of data, for example. Okay, it seems that with 1 month to 5 months of data, you capture most of the predictive power, and which is strange because we know that there's a lot of climatology on the variability of these parameters. I don't know if I answered the question.
Yeah, it sounds like the data collection, data learning it's grabbing onto any of the characteristics. And since this is a long-term ionospheric project where the source of information is actually changing over the year, it's probably noticing the differences. So going longer would just confuse it. It sounds like if you had a minimum, like a 1 month period, and you did it 1 month chunks and then tried 3 months and see how the things merge or where the biggest change is in the ionospheric response to the ionosound, and then find the areas that where they're not changing much, like in, I don't know if it's summer or if it's winter or whatever. That might help narrow down what it's because it's just grabbing on anything it sees changing.
Yes, yes. To your point, there is you see here the error bars from the here we accumulate a lot of predictions and we try to see how the errors distributed in virtual height, which is the units of the ionograms. And as you can see, the first row corresponds to 1 month of data training, and the second row 3 months. So if you go from 1 month to 3 months, you don't get a lot, you gain a lot. You gain some accuracy around higher frequencies, but it's not like a crazy amount. And but what I think is more important, and we talked about this several times with the students, is that we really don't need the system to be perfect. We just need to be better than the alternatives. So I would say that some of the strongest alternatives, if you want to get some prediction of the ionosphere in the next few hours, is IRI or SAMI2. And consistently, we have been outperforming both, but we need some more tests to be sure what is the extent of this improvement.
Because it looks like the graphs you were showing with the errors on the previous slide, one more. The right-hand side is the very high distances. And that's probably the scarcest data in the matrix that it's getting presented, would be my guess. There's not as much data in there about that than the rest of it.
I would say that's probably not extremely related to the availability of data, but with the fact that there is more variability in that region, because the traces of the ionosonde, they can vary a lot in the last part, and also because so if you remember what I showed here, so if you just use a neural network to do a regression to estimate ionograms, you're going to get something like this, because the ionogram the neural network won't know where to stop to give you virtual heights. You need a second system to do that. You need a second system to learn where to stop. And that is more critical when you need to stop, right? Because if you missed for a couple of frequencies, you can get a very large error, right, on the around FOF2. So that may be also related to this.
Very good results, though. That's impressive.
Yes, they look fine so far, luckily. Yeah. Thank you.
Thank you.
Any other question? Is Nathaniel back?
I know he's watching. I don't know if he's dialed in.
I
I
see.
saw his phone thing show up for a second, then it dropped out, so I'm not sure what happened.
Okay.
He's probably still trying to dial in.
Okay.
Oh, there he is, maybe. I wanted to ask on section 2.3.
Yeah.
Just generally the
What's that?
mhm.
A pen? Not that I've seen. What sort of pen?
Dave, your mic's on. The when you have the HMF2, the virtual surfaces, this is kind of outside the present scope, but I've been following this sequence of papers because I'm trying to figure out how to do something similar with some of the work we're doing with the personal space weather station. And I just wanted to ask if maybe I could meet with you at another time to discuss it in more detail.
Yes, I would love to do that. It's so especially if you are interested in the methods that this guy developed, I would love to have somebody to talk about this because these are very tough equations. And I'm very curious about the possibility of using some other tools. So for example, just as a general description of what I'm thinking about is, what he's doing is he's shooting rays, and it's a shooting problem. He tries to get to the receiver. So he has to do it a couple of times and then correct the initial angle, right? The initial K. But to do that, in order to know how to correct it, you need to have another set of equations to propagate the difference in your landing site all the way back to the initial conditions. And those equations are very tough. On the other hand, there's a different approach, which is the following. What you do is you start with a reasonable assumption, and then you say, okay, I'm going to assume that the solution looks like this, and I'm going to put this into the system of equations. Okay, so you put like a parameterized parabola, for example, or parameterized a curve interpolated with Chebyshev polynomial, I don't know. And then you put that into the equation, and when you do that, you remove the differentials. You only have a nonlinear system for some unknown coefficients. So you go from a nonlinear set of nonlinear differential equations to a set of nonlinear optimization problem. And that's something that a lot of people are developing in the trajectory optimization community. These people interested in teaching robots how to fly by themselves, for example. There's a lot of code being developed, very efficient code. And I think that set of tools could be extremely useful for this problem. So yeah, we can talk about this whenever you want. Yeah.
Yeah, that would be great. Could I get your email address? Just
Sure.
put it in the chatter.
Okay, I think I know how to do that. Let me, yeah.
Thank you.
Kike, I wanted to point out that this paper came up in conversation in connection with the AeroVista CubeSat project that we were just talking about on Tuesday.
Mm-hmm.
And I think the idea is that we could fly over the beacons and be picking them up from the top side. This is I don't know if you know about this project, but it's actually a radio receiver vector sensor pair of satellites.
Uh-huh. I'm not aware of this project, but one of the applications that I was interested in, I have zero knowledge about hardware, so I don't know if this is possible. But I was thinking that maybe because my limited understanding of the topside ionosphere, maybe because things are a little bit more regular. You don't have like stuff like gradient drift instability, partly Bunemann things. I was thinking maybe using these approaches with two topside ionozones could be even possible. I don't know, maybe it's related to what you're talking about, but yeah, I think I understand a little bit that what you're trying to say.
Right, because this is relying on things that are being refracted back down to the ground, but with an overflight, you could get the waves that aren't being refracted down. And of course, you'd only have limited times when it would fly over, but could be used to improve models from both sides.
Yeah. Something important. If you review this paper, you are probably aware. In this paper, Dave is using a system in Peru, an HF system in Peru that works just with 2 frequencies. So,
Right.
yeah, in principle, my understanding is that by harnessing the frequency sweep of ionosome, you should in principle have a more robust system. I don't know if you're considering using an ionosome.
Yeah, this would be receive only passive, but it could be,
Oh yeah, okay.
Picks up the same frequencies, but from a different direction. This is something Jim LaBelle and Phil Erickson and Frank Lind are involved with.
I see. Yeah, I would say that the only thing that would worry me a little bit is the parametrization of the ionosphere, because in this paper we had a lot of so if you use just a Chapman function that depends on 3 parameters to parameterize the ionosphere, that's fine, but you're going to lose some physics. If you want to add some more resolution, the problem gets very heavy, very fast. So I think that's a strong problem. And also the problem of how to model collisions is not, I don't know if Dave has like is totally comfortable with the way that he's modeling collisions so far. So that's something that also would need some improvement, especially if you're going to work with low frequencies. Yeah.
Right. Are these in what, 7 megahertz, that area?
I think these are below 3 megahertz, 3 point something and 2 point something. Yeah.
What type of modulation scheme do these beacons use?
What do you, I don't understand what modulation scheme.
The beacons that you were showing in the next slide, are they just continuous wave beacons, or are they, is there any sort of encoding on them, or?
I'm not sure.
I
don't
believe
know.
it's pseudo random codes.
Oh
from
yeah.
the
So
paper.
random code. Yes.
And you said they operate on 2 frequencies?
Yes, 2 frequencies. Yeah, I think I'm particularly interested in, and well, this is the main goal of this small project is not experimental, but computational. So we want to do a bunch of computational experiments.
Yeah, I just remembered now, 2.72 and 3.64 megahertz. We're wondering how they can be in the middle of the handband there. That's in the 80 meter band. But anything for science, right?
Was that in the US or is that in?
This is in Peru.
Yeah, so they don't have that band plan.
Oh, they're not on 80 meters?
I don't know.
I don't know. But these are frequencies that are covered by the ionosome, local ionosome, Viper ionosome. I don't know if that's helpful. Yep. So I'm going to stop sharing my screen then.
Do you know, you also talked a little bit about the Julia instrument that was used to look at this spread F with your model. Do you know any more of the details of the Julia instrument too?
The only thing I know about Julia is that is a coherent backscatter radar, and it measures Doppler of 3 meter structures.
Okay.
So yeah, and it operates it's supposed to be operating like almost every day,
Mhm.
but of course it's not actually every day, but it's a very good. I don't think there's any better data set to study the climatology or the variability of this phenomena.
Hmm.
It's pretty good. Yeah, and all the data is in Madrigal, as you probably know.
Mhm.
Mhm.
That sounds good.
Yeah.
Yeah.
And do you have any comments? I don't know how you guys are doing with the possibility of developing a ionoson receiver.
Well, as I've said, we've been working on this Tangerine SDR, but we're really kind of stuck right now with the chip shortage. So the current plan is we're continuing to develop it, but using these development boards. So it's really not ready now or in the near future.
Mhm.
But the thing we do have working, which if you want something really cheap, the grape software defined radio or the grape receiver we have is quite nice, and it's very cheap, but it's basically a low IF down converter radio receiver that where you take the GPS signal and you take it output from a GPS disciplined oscillator and you mix it in with an incoming signal. So if you need a receiver that's or if you can use a receiver that has fairly narrow bandwidth, that's a really good option.
Okay, yeah, that's
So
good to know.
it depends how much bandwidth you need.
Yeah, I don't know. So that's one of the Marcos, which I showed his picture. He's doing his PhD in Washington, and he knows more about he knows about hardware, and I don't. So I'm going to comment on that. The great SCR.
Yeah, we've been using it. So this is developed by mostly by John N8OBJ on here, and Christina has been leading a lot of the science research efforts with it. And David Kasdan, who's on here too, has been leading a lot of the efforts with it as well. And we've been using it to monitor the Doppler shifts from the WWV transmitter in Colorado. And we can see very nicely traveling ionospheric disturbances that move through this system. Christina's working on a paper with me and with Steve Serwin and Dev, where we're able to see different different modes of propagation coming from WWV to the receiver. So you can see where we believe it's refracting off of the E layer, where it's refracting off of the F layer. We can do time of flight studies with that. So we've been quite successful with that so far. Christina can probably show you some slides, and I have the slides too if you want to see some.
Oh yeah, I'm going to probably talk with Christina some of these days, so you can maybe
yeah, I'll send you our preprint on it, and that summarizes stuff pretty well, has some sample graphs, things like that.
Yeah.
And then in terms of ionosons, excuse me, we've I'm sorry, I'm still recovering here. We have been using software by Juha Virinen, who is up in Tromsø. Are you familiar with his Chirp Sounder 2 software?
I know about his work, but yeah, I don't know about the details of his work.
So what he has, we have an Edis N200 radio receiver, which is a commercial off-the-shelf option you can get for about $3,000, and you pair that with a decent computer, and you can run his software, and it will automatically detect and decode ionospheric chirp sounders. And so I can show you some examples of what that looks like.
Yeah,
Just
what
showing-
I think what one of the questions is, I guess, how many frequencies are required to make the system stable enough?
So this device will listen to all of the frequencies between, say, DC and 30 megahertz.
Okay.
It can sample all of them simultaneously.
Mhm.
And when you do that, you can run this chirp sounder code that will record all of that data, and then it will create these oblique ionograms for you. And so we've been running this system over at my house, actually right where I'm sitting, here, and we've been listening to the chirp sounder in Virginia Beach in Chesapeake, Virginia over here. And these are ionograms that have been made with it. So you can see it. This is a movie that Dev Joshi, who's also on this call, made.
Mhm.
And so you can see, here's the FOF2 changing. I guess people who are there, you can see how much variability you can get with the FOF2 as it changes with time, which I know you were talking about in your presentation before. And then Dev developed some software where you can take all those ionograms and you can just take slices of them at a frequency that you choose, and you can make these range time plots. So now we're looking at just a 4 megahertz slice, and you can see we get this sort of spread F ionospheric irregularity event that's happening here between like 0 and 12 UT. And that's corresponding very well with these irregularities that we're seeing in the Blackstone superdarn data.
Wow.
So this is all this data is being done with just on the sound of opportunity.
Yeah. You said that
So yeah,
this is so the hardware that you're using is exactly the hardware that Juha proposed in his work.
I'm using this commercial off-the-shelf hardware. So this is not what we're developing, but it's essentially functionally equivalent to what we're developing. So you can buy this today.
Yeah, and you're using Juha's code.
Yes.
You can buy it with a lead time.
You can buy it with the lead time.
45-day lead time right now. I just happen to be looking at.
That's better than 99 weeks.
99
Yes,
weeks.
indeed.
You might be able to get one off of eBay faster.
But yeah, yeah, we use a whole bunch of those out in the field too.
Yeah.
Yeah, that's very useful. Thank you.
Yeah. And this is the low-cost magnetometer that we are developing. So Dave Witten and Scotty Cowling designed this board. And then this board here just supports this is the magnetometer chip that you can buy from another company. And this is an example. These are measurements that were taken by Jules Mady in New York, Hillsdale, New York. And these are using the inexpensive magnetometer. And these are measurements taken off of the Intermagnet website from the professional magnetometer in Fredericksburg, Virginia. So there's good agreement there.
Yeah. Yeah.
I think we're coming to the top of our hour. So I'd like to thank you again for coming and talking to our group today.
No, thank you for the invitation. It was
Yeah,
very useful.
yeah, we really appreciate it. And you're welcome to come by anytime. And I think it sounds like you and Christina will be able to have some good conversations in the near future.
Mm-hmm. Yep. Yeah. Looking forward for it. Yeah.
Thank you.
Thank you. Nice to meet you all, and see you later.
Thank you so much.
7-3.
Thank you.
7-3, everybody.
Bye.